Good morning and welcome to section 4.2. Today we're going to go ahead and look at the mean value theorem. Along with doing the mean value theorem, though, we're actually going to remind ourselves of the intermediate value theorem, and then you're going to learn Rolle's theorem, and then we're going to get to the mean value theorem. So let's just quickly recall the intermediate value theorem. Okay, so we are going to suppose that f is continuous. Remember, continuous means you go from one point to the next without picking up your pencil. If this happens on a closed interval, so remember closed means you have closed endpoints, and n is some number in between f of a and f of b, and from a to b is not equal, so your endpoints aren't the same y value, then there has to be some number c where you plug it in and you're going to get a y value out of n. Okay? So basically if I'm going from this point to this point and my y value is in between and I have to be continuous, there's no going around it because I'm continuous. However, if I didn't say we had to be continuous, could I get around this? Sure. I would just have to go ahead and put a jump in here. But since I'm continuous, I can conclude that I have to go past that y value. Okay, so that is our intermediate value theorem. This one's just showing us that it has to happen, and it could happen more than once. Okay, so if you look here, if I have to go from A to B, and in this case, n is this y value, I cover it 1, 2, 3. There are three C values where I get that y value. So if you think back to when we first did this, let's say that we had f of c of 1 was equal to a negative number, and then f of c of 2 was equal to a positive number, and in between here was f of, I should have called this something else, but c of 1.5, a number in between there, was 0. If you're going from a negative number to a positive number, do you have to go past a y value of 0? Yes. That's what we use the intermediate value theorem for a lot. Okay? And what are zeros? Zeros are roots of a function. That's where you cross your x-axis. Okay? So there's the intermediate value theorem. Then we're going to go ahead, Rolle's theorem. It is a theorem that uses three hypotheses. The first one is it has to be continuous, so that's the same as intermediate. This is new, though. It has to be differentiable on the interval from A to B. Not at the endpoints, but just from A to B. If that happens, okay, then there has to be a slope somewhere of a tangent line that is equal to 0. So if you think A and B are equal in this case, if I take the derivative of a constant, do you guys all agree, which I think you do, that the slope is 0? You can also visually see the slope of this line is 0. If A and B are equal here, at some point there's going to be a C where you take the derivative and it's equal to 0. Should be calling this C because we're plugging in C. So that is what Rolle's theorem is. So we're going to use these two ideas in order to conclude how to do example 1. Okay, so it says, prove that x to the third plus x minus 1 equals 0 has exactly one real root. Okay, so what does it mean to have a real root? Well, a root is that you cross your x-axis, okay, just once. Cross x-axis only once. And I usually graph this on my calculator after we've done it, but I can't do that because my calculator doesn't work from home. So if I look at this, I have a part of my function graphed. Does it appear that I have only one real root? Yes, it looks like it's happening right here. There's only one, it appears. I'm not deceiving you by just showing you a part of the graph. There isn't more of it. You could graph it on your calculator and check. So this is all great, and you're like, sure, yeah, that's true. However, this is your keyword, proof. You have to show, using math, or calculus in this case, that there is exactly one real root. Okay? So what we're going to do is we're going to use the intermediate value theorem to find an interval, okay, where you're going to go from a negative number to a positive number. Okay? And then if you go from a negative y value to a positive y value, do you have to have crossed the x-axis? Yes, you do. Okay? So we're going to use that idea. I'm going to go to the next slide. So first things first, in order to use either theorem, it has to be continuous. Do you guys agree that this polynomial is continuous? It's it's a cubic, so yes, and it's a polynomial, so all polynomials are continuous. Now here's the deal with this one. We don't have a closed interval, but we are going to find one. We can make it up. So we are going to make a closed interval, okay? We're going to use the intermediate value theorem ideas to find interval. So I'm going to go back to my picture to get an intuition. So I need to show that I'm going to go from a negative y value to a positive y value. So I actually might make my interval. I'm going to make it from 0 to, does that look like it's happening at 1? Let's see. Ooh, it's actually in between 0 and 1. So I'm actually just going to make my interval from 0 to 1. If you wanted to, you could make your interval -5 to 5 or -1 to 2. I mean, there's so many options. But we are going to create our interval, and in this case, I'm picking those because I see that if I go from 0 to 1, my 0 is in between there, okay? So our interval is going to be from 0 to 1, okay? So using this idea, I'm going to plug those values into my function, okay? So I'm going to find f of 0. If I plug in 0 here, I get out -1. If I plug in 1 to here, we get out 1. So, do I have a root? Is there a value of c where it is equal to 0 if I'm going from -1 to 1? Yes. So, this tells me there must be an f of c equal to 0 in between 0 and 1. Okay, so by the intermediate value theorem, and I could have just wrote IVM if you wanted to, there is a root between x equals 0 and x equals 1. Okay, and here is how we proved the intermediate value theorem. We did f of our endpoints, f of c less than or equal to f of 1, and then we actually plugged in those numbers. Okay, so this, when I plug in f of 0, I get out -1 and 1. Okay, so we know that there has to be a value where f of c is equal to 0 due to that fact. Okay, so that means there's one root. Now the other thing we need to prove is that how do you know it doesn't make a turn and come back? Okay, well, we just got done doing maximums and minimums, and you guys know that when you turn, okay, there's a chance that when I turn, I could come back down and cross the x-axis again. So what I'm going to do is I am going to check for points of turn. Points of turn. I'm going to look for points where my function turns directions or changes directions, and the way I can find those is by taking my derivative and setting it equal to 0 and finding out how many times does this happen. Okay, if it doesn't happen, then we should be good, right? It's only going to go through there once. But if it happens more than that, we have to be concerned, okay? So the second part to our proof is that we're going to take our derivative and set it equal to 0 to figure out how many times we're turning. So we got f prime of x is equal to 3x squared plus 1. If I set this equal to 0, I'm going to find my critical values, which we just got done doing. We're looking for basically absolute maxes or mins, or not even absolute. We're just looking for maxes and mins. Could be relative. Okay, so I'm going to subtract 1, divide by 3. So I have x squared equals -1/3. And if I take the square root, I have a negative. So what this tells me is that there's a positive, negative, two imaginary solutions, but in this case, there are no real solutions, which means there are no critical points, which means there are no changes in directions. So if there's no change in direction, I'm not going to start going up and then turn around and go back down and cross my x-axis again. So that is how I can show that there is exactly one real root. Okay, so then what we can conclude by the intermediate value theorem there is an f of c equal to 0 between 0 and 1. And since f prime of x equals 0 has no critical points, there is no change in direction. Therefore, f of x has exactly one root. Okay, so there is our proof that we have shown. And you could also look at it here, right? There is no critical points. There is no changes in direction. So I'm not going to go ahead and have more than one root. That's why we took the derivative. If I were to take this derivative and say it looked like this, and I would have found this critical point, I would have been able to say, hey, since it changes direction, there's a chance that there's another one. So there might not be exactly one. Okay. So there is that. All right, the next thing is the mean value theorem. Okay, when you think mean, you think, well, in terms of math, it's your average. Okay, so what the mean value theorem is that you have function f and it has to satisfy the following hypothesis. It's got to be continuous on a closed interval and differentiable from a to b. Okay, so not so much worried about the endpoints, but it does have to be differentiable in between. So what it's saying is then there's some number c in AB such that the derivative, okay, your slope at an instant, is equal to your old school slope, okay, which is your average slope. Think about it. They're the same thing. y2 minus y1 over x2 minus x1. Or equivalently, all they did here was they took m times b minus a to the other side. We usually think about it in terms of this though, okay? So mean value, so your derivative is equal to your old school slope. So here's some pictures to kind of help us. Okay, the mean value theorem that says that at some point in the interval, the actual slope equals the average slope. Okay, so one thing, I think I can do it, you guys can do this pretty handy on your iPads, I know, is that we have our endpoints, okay? What we do is we find the slope from here to here, okay? Then what it's saying is, if I copy this and keep it at that same slope, somewhere along my curve, there's going to be at least one more time where that slope's the same. So you can see that that is happening here. Okay, it doesn't happen anywhere else but your tangent line. Okay, so we're finding where our tangent line is the same. So they are parallel, which that's why we're setting them equal to, right? Parallel lines have same slope. So the next one, we go ahead and we look at our endpoints, find the slope from one endpoint to the next, and then they're saying as you go from A to B, somewhere along this curve, there's going to be a tangent line that has the same slope, and you're only touching at one point. So I see right there. And actually, in this case, if I continue along my curve, there is another point right there. So there's 2 points where the tangent line, the slope of the tangent line, is the same as the average slope. Okay, so we're just finding where those points are happening. In order for this to happen, though, it has to be on a closed interval, and it has to be a continuous function. Okay, so let's do this. We have y equals ln of x minus 3, and we are looking from 4 to 9. So we have to show that it satisfies the conditions of the mean value theorem. So the first thing is we have to be continuous. Yeah, maybe let's say on a closed interval. Let's look at our closed interval. Continuous on a closed interval. Are we on a closed interval? Yes, from 4 to 9. They mean the same thing. Then the other thing is, for closed, we got to be on continuous. The biggest thing is you are continuous on this interval. So I don't have my calculator, but ln of x. If I were to just graph y equals ln of x, you could graph it. You could also graph the one we're talking about, but I'm going to start out with this one. This has an asymptote right here, goes through the point 1, 0, and it looks like this. Okay. So looking at this, it's not always continuous. It's continuous for numbers bigger than 0 and onward. For x values, I should say bigger than 0 and onward. But we are looking at ln of x minus 3. So let's think about this. If I graph this, it looks like it's going to the left, but it really means that we're moving it to the right 3. So I can take and move this over to the right 3. Or you could graph it. And now we're going to go through not 1, 0, but 4, 0. We're going this way. So, are we continuous from 4 to 9? From 4 and onward? Yes. You could graph it and look at it as well. There it is. And then the last thing is you have to be differentiable. C, part C. So, differentiable on the interval. That's our question. So what we're going to do is we're going to take the derivative. So our derivative is, it's a chain rule. The outside is ln. The derivative of ln is 1 over x, so it's 1 over x minus 3 times the derivative of the inside, which is just 1. So that's our derivative, okay? And so where is this derivative always exist? Does this derivative always exist? No. It does not, the derivative does not exist when x is equal to 3. However, is 3 in my interval that I'm looking at? No. So am I differentiable on my interval? Yes. So these are kind of like our 3 checklists to use the mean value theorem. Okay? Closed interval, continuous, and differentiable. So we are good there. So now we're actually going to find the value that satisfies the mean value theorem. For f of b minus f of a, all over b minus a. So what we're going to do is we have our derivative. Sorry, I don't know why that changed. Okay, we have our derivative. We just took it on the other side. We had 1 over, I'm going to write down f prime of x. But you see how it wants f prime of c is equal to this? So we're going to just write down what it is, and then we'll plug it in with the value of c. And then it wants f of b minus f of a all over b minus a. So this is really asking us to find our 2 points and then find old school slope. So our endpoints, this is your a, this is your b. So we are going to find f of 4 equals ln of 4 minus 3. If you type in ln of 1 on your calculator, you will get out 0. Then if you plug in 9, ln of 9 minus 3, just finding my point, we'd have ln of 6. That is not an exact answer. Okay, so we're going to leave it as ln of 6. Okay. So now we're going to set it up. This is my derivative. This is my f of c. So I'm going to write down, we really have 1 over c minus 3 is equal to f of b minus f of a all over b minus a. So ln of 6 minus 0 over 9 minus 4. Then I have 1 over c minus 3 equals ln of 6 over 5. And now what our goal is to do is to find what c is. Okay, so I am going to times both sides by, actually you could, it's a lot of multiplying, but essentially I don't want this in the denominator, so you could essentially flip both sides. That's what will happen. But we can go through the steps if you want to. You would times both sides by c minus 3 on both sides, so you'd have 1 equals ln of 6 times c minus 3 all over 5. And then I'm trying to get this c minus 3 by itself, so I'm going to times both sides by 5 and divide by ln of 6. So we have 5 ln of 6 equals c minus 3. Sorry, wrong button. And if you look here, isn't that what I would have gotten if I went from this step to here if you would have just flipped both? But you can do the math. And then I'm just trying to get c by itself. So c, I would add 3 to the other side. So c equals 5 ln of 6 plus 3. That would be our c value on there. So we have some function, and we're looking at that interval, and that is where, that is the point where that would happen. Okay, so something like this. We are looking at it from 4 to 9. So let's just say right there. I'm gonna move this a little bit. Sure. And then what we did was we found the point in between there. So if you type in 5 divided by ln of 6 plus 3, it is 5.791. So somewhere along there, they would have a tangent line. And I know mine isn't drawn accurately, but there's a point on here, maybe graphically, visually. It's kind of hard to see. Would touch probably right there, okay? So if you type it in, you could also graph it on your calculator. I would recommend it. Graph ln and just look at it from that part. And then kind of say, oh, if I were to draw a tangent line, would it be parallel there? So that's what you are finding with the mean value theorem. Okay. All right, here's another one. Show that it satisfies the mean value theorem. So we have x cubed minus x. First things first, is it on a closed interval? Yes. Yes, and the interval is from 0 to 2. And then is it continuous? Yes, it's a cubic, which is a polynomial. And all polynomials are continuous. And then 3, differentiable. So the derivative is 3x squared minus 1. So is this always exist? Yes, it does. So it doesn't even matter about the interval. So yes, it is differentiable. So now that those 3 things check off, I can go ahead and use the mean value theorem. So we are taking our derivative and setting it equal to our old school slope with our endpoints here. Okay. So our derivative was 3x squared minus 1. And then we had to find our points. So we plug in a and b to our equation to get our points. So we plug in 0. 0 cubed minus 0 gives me 0. So that's my point, 0, 0. And then we do f of 2. 2 cubed minus 2. So we would have 8 minus 2, which is 6. So we really have the point 2, 6. So then you take your derivative of c and set it equal to your old school slope. Okay, y2 minus y1 over x2 minus x1. So we have 3c squared minus 1 equals 6 minus 0 over 2 minus 0. 3c squared minus 1 equals 6 over 2, which is 3. And then I'm going to solve for c squared. So I'm going to add 1 to the other side. So I have 3c squared equals 4. Divide by 3. So I have 4 over 3. Then I take the square root. So c is equal to plus or minus the square root of 4 over 3. Okay? Then we should always check that it's in the interval. I'm looking from 0 to 2, so I know I'm not going to include the negative answer. But if I take the square root of 4 over 3, it's 1.15, and is 1.1547 in between 0 and 2? Yes, it is. Okay, so no negatives are in between 0 and 2, so our only c value is the positive 4 over 3. And you can leave it like that. You don't need to rationalize. Okay, so there is our c value where that happens. Example 4. A car drives 200 miles in 3 hours. According to the mean value theorem, so we can use this idea of slope to think about it. At some point was a car traveling at least 60 miles an hour, 65 miles per hour, and 70 miles per hour. So we have to think about this in terms of average rate of change. AKA old school slope. Slope. Okay. When you left the house, time was 0, you had traveled a distance of 0. 3 hours later, you have traveled a distance of 200. So what it's saying is find the average rate of change. So our slope would be 200 minus 0 over 3 minus 0. So we'd have 200 divided by 3, which gives us 66.6 repeating miles per hour. So basically what this tells us is if you leave your house and you instantly started driving one speed for the next 3 hours and you stayed driving that speed the entire time, you were driving 66.6 repeating miles per hour. However, that's not practical, but that was your average rate of change. Okay. So what this asks is, at some point in the instant, was there an instant, so tangent line, was there a time you were traveling at least 60 miles per hour? Clearly, yes. At some point, were you traveling at least 65? Yes. At some point, was the car traveling at least 70 miles per hour? We cannot conclude that one. Not necessarily. Most likely, but we can't conclude it based on our average rate of change. You could be going, probably at some point you had to be going more than 66.6 repeating, but you can't conclude it based on what we have here. We do know we were going faster than 60 and 65, but not necessarily 70. Most likely, but not necessarily. Okay, so there's that idea with a car. Last problem we have here, and I think it's very similar to the last few problems on your homework, but we have suppose that f of 0 is equal to -3. Our derivative of x is less than or equal to 5 for all x values. Okay, so our slope, the biggest slope, is 5. How large can f of 2 possibly be? So we're trying to figure out the biggest value that it can be. Okay, so we are going to go ahead and bring in our mean value theorem. So that is f prime of c equals f of b minus f of a all over b minus a. So we're going to have our derivative, okay, and then we have to have 2 points on our closed interval. So what would our interval be? What would our a be and what would our b be? Well, we got 0s and 2s, so a will be 0 and b will be 2. Okay, so let's plug it in. We have our derivative at c will be f of 2 minus f of 0 all over 2 minus 0. So what do we know? We know that our derivative is always less than or equal to 5. Okay, so what's the biggest it could be? If we're trying to figure out how large it can be, the biggest it can be is 5. So we're going to plug in 5 for that. Then f of 2. Do we know what our f of 2 is? That's what we're trying to figure out, so I'm going to leave it as f of 2. Minus f of 0, -3, all over 2 minus 0, so 2. So this will give us f of 2 plus 3 over 2. And what our goal is, how large can f be? Well, we're just trying to figure out f of 2. So we have to times both sides by 2, so I have 10 equals f of 2 plus 3. And then I would subtract 3, so f of 2 equals 7. So the biggest our f of 2 could be, since we plugged in the biggest possible slope, would be 7. All right, so your homework, page 285, or PDF 313, those are the problems. I am expecting you to have this video watched, have looked at the homework. I will take questions on your homework tomorrow. Otherwise, have a good day, and I will talk to you later.